Hi, so today we'll be going over power series, that's sections 11.8 to 11.11. Before we begin, we'll just review really quickly what is a power series. Well, it's a series that's got x, or x subtracted by a constant of a, to a power in terms of n. It doesn't necessarily have to be n itself. It'll usually have a coefficient in front of it. We can also view a power series as the infinite polynomial represented by the expansion of that power series, and we're going to be going over how to convert between the two. So remember that your interval convergence is the set of x values for which a series converges, and that your radius of convergence is just going to be half of the width of that interval, and you can see why here. We also have some pretty easily memorized formulas for functions as power series, the first being the one you see right here, that's the basic one. We can also get 2 and 3 just by integrating forms of that original formula.
So in this problem, you start by knowing that the function and its derivative share the radius of convergence. So you can first start by doing the ratio test, which is what gets you x plus 1 to the n plus 2 power over n plus 2 times n plus 1 divided by x plus 1 to the n plus 1 power. And then once you take the limit, the n terms cancel out and you're left with absolute value of x plus 1 is less than 1. And then once you divide up the absolute value, you can get two equations where x plus 1 is less than 1 or x plus 1 is greater than negative 1. And then your two endpoints are 0 and negative 2. So to test those to see if they're convergent or divergent, you have to plug them into the derivative, which is right here. And then for both series, you get diverges by divergence test because 1 to the n just yields a constant, and then negative 1 to the n does the same.
So here we have this series, and we've got to write its function equivalent. Noticing the 2n plus 1 in the denominator is going to be really helpful because remember that arctan of x is the only memorized formula we know that's got that 2n plus 1 in the denominator. So if we can make our series become arctangent, then we have a really good bet of getting the right answer. Knowing that, we can simplify the numerator to combine the 256 to the n with x to the 4n. We'll raise both to the same power, remembering that 256 to the n is the same as 4 to the 4n. We can now combine them. That said, in order to combine our 14x squared with the 4x to the 4n, they gotta have the same base, so we'll pull a 7/2 out to achieve this. Now we have our series, but our 4n plus 2 needs to be a 2n plus 1 to fit with our arctan series formula. So we'll divide that by 2 and square the base, leaving us with this right here. We'll also substitute the x in arctangent of x for arctangent of 16x squared, and we'll stick the 7/2 up front, leaving us with this formula. Before we go over 11.10, remember that a Taylor series is really just a power series centered at a in this form right here. A Maclaurin series is just a specific form of a Taylor series, and that's centered at a is equal to 0. In addition to the three formulas we already have for functions as power series, using this knowledge, we can also figure out e to the x's formula, as well as cosine of x's and sine of x's.
The point of this problem is to convert a constant into power series using one of the Maclaurin formulas that we've already memorized. When looking at this problem, negative 55 over 2, it's important to keep the trig formulas in particular in the back of our mind because they're some of the easiest to convert constants into. Now, the first thing you should notice is the 2 in the denominator, because if we factor out the negative 55 and have it negative 55 over 1/2, we can remember our unit circle, and that sine of pi over 6 is equal to 1/2. Now, you can also use a cosine, or you can use 7 pi over 6 or 11 pi over 6. Those are all alternate methods in order to solve this problem. But if we continue with sine of pi over 6, we now have negative 55 times sine of pi over 6. Now we have the sine Maclaurin formula memorized, which is the sum of negative 1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial. If we plug the pi over 6 into the x value, we now have negative 55 times the sum of negative 1 to the n times pi over 6 to the 2n plus 1 all over 2n plus 1 factorial. Now, Moving the 55 in is simple, you just add that into the numerator, but now we have a negative on the outside. But if we treat that as a -1, we now have -1 to the n plus 1 in the exponent slot. And that's how you convert -55/2 into a power series.
Okay, so for this problem, they ask you to find a Maclaurin series for g of x is equal to cosine of e to the x. And you know the series for cosine x, which is the summation from 0 to infinity of x to the 2n times -1 to the n, all divided by 2n factorial. So you just plug in e to the x as your x value, and then you're left with summation from 0 to infinity of -1 to the n e to the x all to the 2n divided by 2n factorial. So for part B, they ask you to write the Maclaurin polynomial to the 6th degree, and you see that e to the x is raised to the 2n power, which means n equals 3 will get you to your 6th degree. So you plug in n equals 0 as your first term, and you get 1. N equals 1 will get -e to the 2x over 2 factorial. N equals 2 will get you e to the 4x over 4 factorial, and n equals 3 will get you -e to the 6x over 6 factorial. Then they ask you to use that polynomial to approximate cosine of e squared, and since that polynomial is for e to the x, cosine of e to the x, you just plug in 2 as your x because it's e squared, and you're left with 1 minus e to the 4th over 2 factorial plus e to the 8th over 4 factorial minus e to the 12th over 6 factorial. And once you plug that into your calculator, you get about -128.141. And then they ask you to explain why the approximation is so horrid. And that's because the Maclaurin series for cosine of e to the x is centered at c equals 0, but cosine of e squared is nowhere near that graph, as you can see in the representation. It only follows the graph for the beginning and then it strays. So the graphs are nowhere near each other, which is why the approximation is so horrid.
Recall that we have two main types of error in this chapter. Right now we're going to be focusing on Lagrange error, which asks how far a Taylor polynomial is from its corresponding Taylor series on a specific interval. It has a formula that looks a lot like this, where m means the maximum of the n plus 1th derivative of x on the interval. And remember, avoid making the mistake of thinking that the x that you're raising to the nth plus 1 power is necessarily the same x that you're plugging in when you're finding the maximum. The x that you're raising to the nth plus 1 power should be the furthest x from your a value, which in this case for a Maclaurin series would be 0 and for a Taylor series would be a. Whereas your x that you're plugging in for the max is going to be the x that's going to produce the maximum value of f to the n plus 1 of x on the interval. Since the first part of the problem is very similar to one that we completed already in class, we'll be looking straight to 5b, which wants us to find the 5th degree Maclaurin polynomial for the given function. So here we're going to convert it using our formulas into its power series form, and then we're going to notice that when we plug in specific n values, we're just going to get the values that we see right here, 1 plus x plus 1 half x squared plus 1 6x cubed plus 1 24th x to the 4th plus 1 over 120 x to the 5th. So now, using Lagrange error, we're going to find the error of the 5th degree Maclaurin polynomial in part B on the interval -3 to 1. So using our formula from earlier, we have our 5th degree, our R5, being less than or equal to m over 5 plus 1 factorial times the absolute value of x to the 5 plus 1 power. Simplifying, we notice that we're going to take our x that is furthest away from a, which is 0, so we'll pick -3, giving us this nice formula right here. We also know that m is the max value of the 6th derivative of f of x on the interval. That's just going to be at 1, because that's going to give us our maximum value, being that e is greater than 1 over e cubed. So our m is going to be e, leaving us with this nice error right here.
So for this problem, the purpose is to use power series in order to help you take the limit. Because in this case, if you plug x equals 0 into your x values, you're going to have a 0 in the denominator, which doesn't work out for your limits. So what you're trying to do is, in order to use the numerator to cancel out with the x squared in the denominator. So how you can do this is using Maclaurin series of the natural log of cosine of x and using those values to cancel with the x squared. So if you create a t-chart with your n values and your f of n of x values and your f of n of 0 values, you can see which ones will go to 0 and which ones you can actually use to help cancel out with that x squared. So your first two Maclaurin values go to 0, so you don't actually get one you can use until your second n value, which is negative secant squared of x. And plugging in your 0 value, you get negative 1, which is negative 1/2 x squared. Your second value is n of 4, which is equal to negative secant 4x, which goes to negative 2, which then becomes negative 1/12 x to the 4th. So if you write those values into your numerator, you can then cancel them with the x squared and the 11, which will give you the limit as x goes to 0 of negative 1/22 minus 1/132 x squared, which when you then plug 0 in, you'll only have negative 1/22 left over, because all the other terms after that will all have x's, which will make them go to 0, so the only thing you have left is negative 1/22.
Well, we know how to find Lagrange error, so now we'll move over to the alternating series error of functions as power series. This is usually going to involve an integral, and it will obviously always involve an alternating series. We're going to want a number 7 to approximate the integral using power series with an error of less than 0.00001 of this integral right here. We'll plug tan negative 1 of 7x, plugging 7x into the formula that we memorized for tan negative 1 of x as a series. And doing that, we can also move the x squared into the series itself, leaving us with this integral right here. Actually, once we integrate that, we're going to end up with this right here, just using our power rule. And if we plug 0 in, we know that we're actually we're just going to end up with a 0. So we can plug in the 0.1, leaving us with a 10 to the 2n plus 4 in the denominator. When we create this chart right here, we see that each of the values is going to give us greater than the error we want until we get to n equals 2, and that's going to give us less than the error. So we know that we're going to need to use n equals 0 and n equals 1 added together to give us the partial sum that's going to give us the error that we want, or less than the error that we want, I should say. And that's going to be 7 over 10 to the 4th times 4 minus 7 cubed over 10 to the 6th times 18. So thanks for watching, and just remember to refer to our worksheet and quiz for more practice. See you around.